The top of your screen moves toward the future faster than the bottom. To understand why, we need to explore 3 amazing ways to travel through time. Building a time machine to go into the past remains a fantasy reserved for science fiction. However, it is possible to embark on a journey through time right now, all while staying at home. For that, you simply need to stay there, without moving and do nothing. Because you are currently, like everything around you, at every moment, traveling through time, heading toward the future. Over the past year, you have thus moved forward by 1 year in time. Okay, so far, nothing too surprising. We're not exactly on the most exciting time travel adventure. But to spice things up, what we're going to do in this video is try to get to the future faster than everyone else. To do this, you only need 2 things: gain altitude or move. Let me explain. Let's begin with movement. Over a century ago, Albert Einstein revealed a peculiarity in nature's laws. To travel through time and reach the future faster than others, you just have to move faster than them for a while, then come back to where you started, where you left them. And if this is possible, it's because space and time are actually just 2 aspects, 2 components of one and the same thing, the space-time continuum. In other words, in our universe, the faster you move through this space-time, the faster you travel toward the future. Because the way time flows for someone or something is closely linked to the speed that thing has. To try to get a grasp on this statement, let's take a concrete example. Imagine for a second that we set off into space for a 5-year journey, traveling at 99% of the speed of light before returning to Earth. Let's set aside the fact that the acceleration needed to reach such a speed in a reasonable amount of time would turn us into shapeless mush. It would require enormous energy to accelerate the ship. That's the beauty of thought experiments. We can physically allow ourselves anything, so, of a point like nature. After exactly 5 years traveling through space at 99% light speed, we return to Earth as agreed. Except that when we return to our starting point, for everyone who stayed on our planet, we're quite a bit late, to say the least. From their perspective, it's been over 35 years since we left, so what happened? Well, because of our very high speed of travel through space-time, our own time simply shifted. We didn't travel to the future at the same rate, but from our view, nothing felt slow. That 5 years traveling through space weren't in slow motion. 5 actual years passed on the ship. Whereas, on the other hand, for those who stayed on Earth, more than 35 years have passed since we left. Which means that a hypothetical ship taking off from Earth in 2023 and traveling at 99% of the speed of light would take just 5 years to reach our planet by 2058, while for everyone who stayed there, a little more than 35 years would have passed. In short, time is unique to each person, stretching or contracting based on our movement through the space-time continuum, and this effect grows stronger as speeds approach the speed of light. If we traveled for 5 years at 99.5% the speed of light, almost 50 years would pass on Earth by the time we returned. At 99.99% of the speed of light, 353 years would have passed. At 99.9999% light speed, 11,180 years would pass on Earth. In short, as you approach light speed, the time difference grows dramatically. If all these statements seem completely counterintuitive to you, don't worry, that's perfectly normal. Living our daily lives at low speeds, we can't personally experience these effects, known as relativistic. And we intuitively think of time as absolute, meaning it unfolds in the same way for everyone. In fact, for you to be able to experience these time-shifting effects, you would need to be able to reach at least speeds on the order of 1/10 the speed of light. Maintaining that speed for 5 years would result in about a week's time difference upon returning to Earth, but we're still far from achieving such speeds. The fastest humans relative to those on Earth are the Apollo 10 astronauts, whose spacecraft reached almost 40,000 kilometers per hour, returning from the moon. A huge speed, but still over 25,000 times slower than light. So you must be wondering, what proves to us that all these stories aren't just mind games? Well, to test these theories, which might seem like complete jokes, and to check that they really match the way nature behaves, scientists have created hundreds of increasingly fascinating experiments. One of the most well-known involves using clocks that can measure a very large number of very short durations, so-called atomic clocks that will keep the pace. Counting the number of times for a given atom, the electrons move from one energy level to another. On an infinitesimal scale, these puzzling phenomena happen very rapidly and consistently. Thus, in a cesium atom, the electrons, in a way, keep the beat at a rate of 9,192,631,770 oscillations per second. So, between the moment a particle of light leaves your screen and the moment it reaches your retina, an electron in a cesium atom has changed its energy level almost 10 times. Using these stroboscopic oscillation behaviors, researchers have developed clocks with unmatched precision. And armed with these extreme metronomes, sensitive to the slightest variations, they have been able to carry out thousands of experiments, all of which have confirmed this intimate link between the speed we possess and the passage of time. It has been shown that after 6 months on the space station, traveling at about 27,000 kilometers per hour around Earth, an atomic clock, initially synchronized with one on Earth, displays its time upon return, a difference of 1 microsecond less than the one that stayed on solid ground. This also applies to everyone who stayed on board. This calculation showed that cosmonaut Sergei Krikalev spent 803 days in space, by far the most, the fastest human to travel into the future. During his missions, Sergei aged 22.68 milliseconds less than those on Earth. These phenomena of time shift are also observed in particle accelerators, where it is found that, from the point of view of those studying them, these particles decay at a slower rate when they are propelled at speeds close to that of light than when we observe these same decays at rest. You probably think this all sounds strange and far-fetched. If not, then you're the strange and far-fetched one. Got it. Hold on, this is just the beginning. Because if, to get to the future faster, you don't feel like moving, you can also simply stand up, gain a little altitude. Indeed, to the time shift that occurs when we move through space-time, another delightful peculiarity is added. As a result, the top of your screen moves toward the future faster than the bottom, just as your head moves toward the future faster than your feet. Unless you're watching this upside down. No, I haven't taken anything. Nature is just wild. The reason for this oddity, once again highlighted by Einstein, is that the fabric of space-time is warped by the presence of significant mass. Mass, by dictating to space-time how it should curve, also tells time how it should flow. Again, many experiments and observations have confirmed that being close to a massive object slows down the flow of your own time compared to those who are farther away from it. Of these experiments, the simplest to grasp is the one with 2 orientations. Atomic clocks and the massive essential Earth, vital for survival, but trampled daily. 2 perfectly synchronized atomic clocks are placed side by side, then one clock is moved to spend several dozen hours one floor above the other. When the 2 clocks are brought back together, it is always found that they are very slightly out of sync, exactly as the theory of relativity invariably predicts. Those on the lower floor, exposed to slightly stronger gravity during the experiment, are just a bit behind those who spent 10 hours upstairs. Simply put, time passes more slowly at sea level than in the mountains. Because the effect of time slowing down at the surface of a massive body decreases as you move farther away from it. Every day, a person living at an altitude of 1 kilometer ages 0.000010 seconds more than someone living at sea level, and that's for each kilometer of altitude. Time passing faster as you move away from Earth's surface has another delightful effect. Standing for a minute means your feet experience time 10 femtoseconds less than your head, which is notable. You must find this contradictory to astronauts, who spend long periods living at about 400 kilometers altitude. Exposed to a weaker gravitational field, they return slightly younger than those who remained on Earth. The thing is, each time, both effects come into play. For astronauts, the speed-related effect is much greater than the effect from their distance from Earth's mass. Understanding these relativistic effects isn't just a treat for the mind. It's also very useful in our daily lives, allowing us, for example, to use devices that many of us rely on every day. To know precisely where to go and which route to take, they use global positioning system. Because when you use such a positioning system, it's necessary to take into account the tiny time differences that exist between each clock on board the satellites and the one in your phone. In short, to synchronize them. Global positioning system satellites experience relativistic effects due to their orbital speeds of about 14,000 kilometers per hour, and as a result, their days are shorter than ours by 7 microseconds. And on the other hand, being nearly 20,000 kilometers above the ground, they are subject to a much weaker gravitational field than we are. So their proper time flows slightly faster than that of your phone left on Earth. Due to this distortion, time there moves 45 microseconds faster per day than here, In the end, under the combined effect of both, the time distortion caused by their speed slightly compensates for the one due to their distance from Earth. And their day is accelerated by about 38 microseconds compared to ours, 38 microseconds. It's a negligible value, but it must be considered to synchronize all these devices' clocks. Otherwise, our global positioning system would give us meeting points with an accuracy drifting by about 10 km per day in our daily lives, unless you're an atomic clock. Time distortion from a slight movement in space-time or climbing a stool or stepladder is extremely subtle. Luckily, we still have a way to time travel without using any technology. You've definitely accomplished that while sitting here with me, because since the beginning of this video, you have traveled about 20 minutes into the future. However, this journey was slightly shorter for your feet. The ideas developed by the theories of special and general relativity are absolutely mind-blowing. They shake up your view of the world and require a certain effort to be fully appreciated.